Imagine if everything that exists in the universe, from the smallest particles to the largest galaxies, was the result of something simple and fundamental. Not a collection of loose pieces, but different manifestations of the same essential element. That's what string theory proposes. A bold hypothesis that suggests the foundation of reality is strings vibrating in different patterns. Modern physics works with two major frameworks. General relativity explains the behavior of the cosmos on a large scale. Quantum mechanics, on the other hand, governs the world of subatomic particles. The problem is that these two theories, while precise, don't fit together when we try to understand the universe as a whole. And it's precisely in this gap that string theory emerges as a possible solution. If you've always thought this topic was difficult or reserved for specialists, you can set that idea aside. Today, we're going to dive into this universe with clear explanations, simple comparisons, and a good dose of curiosity. The goal is to show that even the most abstract concepts can become understandable when presented the right way. But what makes this proposal so revolutionary? String theory is considered one of the most daring and fascinating ideas in modern physics. It proposes that, instead of point particles, everything that exists in the universe would be composed of tiny one-dimensional strings. These strings vibrate in different ways, and each vibration pattern gives rise to a distinct particle. Instead of isolated atoms or invisible fields, we have a universe made of cosmic music, where each particle is a note, a proposal that completely changes how we understand matter and energy. The main objective of this approach is ambitious: to unify all fundamental forces of nature into a single framework. This includes gravity, electromagnetism, and the strong and weak nuclear interactions. Physicists often refer to this unification as the theory of everything. If it's correct, it could explain both the behavior of a black hole and that of an electron spinning around an atom's nucleus. Such a model would bring order to phenomena that are still treated separately today. But here comes a surprising twist. For this unification to work, this proposal requires a universe quite different from what we're used to imagining. According to its calculations, we don't live in just 3 spatial dimensions and 1 temporal. There are at least 10 dimensions, with 6 of them curled up upon themselves, beyond our perception. It might seem strange, but these extra dimensions are essential for the strings to vibrate in different ways, generating all the diversity of particles and forces we know. The origin of this concept is directly linked to an impasse faced by modern physics. General relativity, formulated by Einstein, precisely explains the behavior of space-time, gravity, and celestial bodies on a large scale. On the other hand, quantum mechanics effectively describes the microscopic world, where particles like electrons and photons operate. Both work very well, but in different contexts. Here's the issue. The problem arises when we try to apply both at the same time, as in black holes or at the beginning of the universe. Here's the crucial point. This conflict becomes evident because gravity doesn't fit into the rules of quantum mechanics. While the other fundamental forces behave well in the standard model of particle physics, gravity escapes this control. Result: we still can't describe gravitational interaction at the quantum level in a satisfactory way. Einstein treats gravity as space-time curvature. The quantum world, however, demands something more discrete and probabilistic, which generates contradictions. It was facing this challenge that our proposal emerged as a possible bridge between these two worlds. It offers a new language to describe both gravity and subatomic particles in the same system. By proposing that all fundamental entities are strings vibrating in multiple dimensions, this approach opens the way for a more unified framework. And even without experimental proof, its value lies in providing a logical structure to solve one of the greatest dilemmas in modern physics. Now, to better understand where this theory fits, we need to talk about something fundamental. The Standard Model is one of the most remarkable achievements of modern science. It successfully describes 3 of the 4 fundamental forces of the universe: electromagnetism, the strong nuclear force, and the weak nuclear force. With it, we can predict the behavior of subatomic particles with extreme precision. It's thanks to this model that we understand the functioning of atoms, nuclear reactors, and even electronic devices. But there's a key piece missing from this puzzle. And here's the major limitation. The force of gravity, curiously, is not included in the Standard Model. The reason is simple. It doesn't behave like the others at very small scales. While the other forces can be quantized with relative ease, Gravity resists this type of approach. The idea of a graviton, a hypothetical particle that would transmit gravity, has already been proposed. However, to this day, no one has managed to detect this particle or confirm its existence directly. This impasse makes it clear that the standard model, however precise it may be, is still incomplete. It works well within the world of particles, but fails when trying to describe the universe as a whole. And it's precisely this limitation that led physicists to search for a more comprehensive theory, something that could unite the known forces and still include gravity at the quantum level. This is where string theory begins to show itself not just useful, but perhaps necessary. Let's get to the heart of the matter. The central proposal of this theory is simple, but profoundly transformative. Instead of treating particles as structureless points, it suggests that everything is made of tiny strings that vibrate. Each vibration pattern generates a different particle, with specific mass and charge. An electron would be a string vibrating in one way, while a quark would vibrate in another. In other words, the differences between particles don't come from what they are, but from how they vibrate. And here's something impressive. These strings are incredibly small, with an estimated length close to the Planck scale, about 10 to the minus 35 centimeters. It's so small that no current microscope could see it. For this reason, even if this structure is everywhere, it remains invisible to our senses and instruments. Still, the theoretical impact of this idea is enormous. It transforms matter, forces, and even space-time into manifestations of fundamental vibrations. What really changes everything is how this approach transforms our vision of the universe. Instead of a collection of isolated particles, we have a complex and interconnected vibrational system. The strings don't just generate matter, but also interact through quantum fields and fundamental forces. Result: it offers a more unified explanation for the functioning of the cosmos. And the more this proposal is studied, the more it seems to align with patterns that physics already knows, even if still incompletely. But here comes a fascinating detail. In string theory, there's an important distinction between two types of strings: open and closed. Open strings have loose ends and can vibrate in ways that explain well the three fundamental forces known so far. That is, electromagnetism, the strong nuclear force, and the weak nuclear force. They help represent particles like electrons, quarks, and neutrinos. On the other hand, closed strings form continuous rings with no beginning or end, and open doors to new possibilities. And here's the key point. Closed strings are the main candidates for describing gravity at the quantum scale. When they vibrate in certain patterns, they generate properties compatible with gravitons, a hypothetical particle that would carry gravity. This is one of the great promises of this approach, managing to explain gravity without having to leave the quantum field. Unlike other approaches that treat gravity as something separate, here it emerges naturally as part of the same system. The presence of open and closed strings in the same model shows how versatile this theory is. Instead of depending on different laws for each force of nature, we have a unified explanation based on shapes and vibrations. The same structure, depending on its mode of vibration, can generate different particles and interactions. This reinforces the idea that, at the base of everything, the universe may be much simpler than it seems. Prepare yourself for something that might seem like science fiction, but is pure mathematics. One of the most surprising proposals of this approach is that the universe may have more than 4 dimensions. We're used to 3 dimensions of space and 1 of time, which together form what we call space-time. However, this proposal suggests the existence of 10 dimensions, with 6 of them invisible to us. They would be present since the origin of the universe, but compressed at extremely small scales. For this reason, they remain beyond the reach of our senses and instruments. And here's something crucial. These extra dimensions aren't an optional detail. They're fundamental for the strings to be able to vibrate in varied patterns and generate different particles. Without these dimensions, the theory's equations simply don't work. The mathematics demands this additional space to account for the complexity of interactions. Even without direct evidence, physicists take this possibility seriously, precisely because it solves several gaps that other theories can't fill. The idea of curled dimensions might seem difficult to imagine, but it's part of a coherent logic. It's as if we lived on a sheet of paper that's folded in directions we can't perceive. Our vision of the universe is limited to the surface, while other directions would be hidden at deep levels of reality. Understanding these dimensions might be the key to discovering why the forces of the universe work the way they do. Now we come to a delicate point. Despite being a promising theory, string theory has not yet been proven experimentally. The main reason is the size of the strings, which would be much smaller than any current technology can detect. They would exist at a microscopic scale known as the Planck length, extremely below what we can observe with particle accelerators. Therefore, there's no way to directly confirm their existence, at least for now. The situation is similar for extra dimensions. Although they make sense within the calculations, they're also beyond our technological reach. No current experiment has managed to detect signals that prove the presence of these hidden dimensions. This doesn't indicate that the theory is wrong, but rather that we're still far from testing its predictions objectively. This is one of the biggest challenges faced by any proposal that goes beyond the standard model. Even so, many physicists continue to bet on this approach due to its mathematical consistency. It doesn't conflict with what has been observed so far and offers solutions to problems that other theories don't solve. Furthermore, it's one of the few viable candidates for so-called quantum gravity, something science has been seeking for decades. The lack of direct evidence doesn't invalidate its potential. It just shows that we still have much to discover. We then reach a fascinating conclusion. String theory is, today, one of the strongest candidates for unifying the laws that govern the universe. It attempts to bring together two worlds that, until now, functioned separately: general relativity and quantum mechanics. By proposing that everything is formed by strings vibrating in multiple dimensions, it offers a profound explanation for the origin of matter, energy, and even space-time. It's not just a mathematical theory, but a new way of seeing reality. Even without experimental proof, this proposal continues to inspire research, debates, and new ideas. It shows that the universe may be much more complex and fascinating than we imagined, and that, behind the solid appearance of matter, there may exist a dynamic, invisible, and interconnected vibrational system. For those seeking to understand the fundamental nature of things, this is an irresistible invitation. After all, exploring the unknown has always been part of the scientific essence. Now, the question remains: what if the theory is right? What else can't we see yet due to limitations of our perception and our technology? Could other dimensions influence our reality in subtle ways? These are reflections that still don't have definitive answers, but that could transform the way we see the world. If you enjoyed the content, subscribe to the channel, activate notifications, and keep following. Because knowledge is just the beginning.